Hey guys, so today I'm going to be doing a Python code on number recognition using neural networks. So the main libraries I'm going to be using are PyTorch. So I'll be writing the code first and then I'll explain it to you so that it's easier to follow. And those who just want the code, you can just take it as you want. So first I import necessary library. So the important libraries are imported. Now I'm writing a code to check if my GPU is being used or uh, my CPU. This code checks which device is being used and prints it out. So when I'm running the code, I'll know if my CPU is being run or my GPU is being run. Now I'm gonna write the hyperparameters here so that I can easily manipulate them instead of individually doing it in the code. I just have it here. So the batch size, for now I'm taking it as 64 because my system can handle it. Learning rate, I'm putting it as 0.01. Sorry, 0.1. And then number of epochs. So since based on my experience with this code, 5 epochs is more than enough for me. So if I do need to change the code, I can just manipulate the hyperparameters here rather than go into the code deeply and check it. So it's easier for me to do this. So now I need to do image transformation. That line, what it does is it uses the transform functions in torch vision to convert the image into the type we want and sends it to the tensor, and it also normalizes it. Wait, so now that that initial stuff is done, now I need to download the data set. So I'm using a MNIST data set, so I'm going to download it from there. So this is a I'm going to have one for train and one for test. So I need to train this one. So I will put train true. Since I need to download it, I put download is true since I don't have it with me in the local thing. Now, what transform I'm going to use since I created a function here. I'm going to use the same function. Transform is equal to transform. So this uh, that is my training data set. So using torch vision, I go obtain the data from MNIST data set, download it, I label it that it needs to be trained, and I also implement the image transformation. Now the same code I will type for the test data set, but this I won't need to train. Put train is false. Download, but I do need to download this because this is what is going to be testing my model if it's running well or not. True. Transform, I'm going to use the same transform. So now that I have downloaded the dataset, I need to train them. I need to load them into the data loader and then train them by writing the model. So for loading, first I need to load the training data. So I'll name it as train loader. So it's better to give variables with the names that relate to the ones you want to. So it's easier to when you look back, it's like, okay, this makes sense. This is what it's for. So I'll use the util function of torch data loader. So now the data set I'm using will be the train data set. So I have to write that, whichever variable you've set it for. In case you're using a different one, you can set that. The batch size. So here's where the hyperparameters are. Since I put it on top, I don't need to manipulate it here. I just write that variable here. And I am going to shuffle it for training load. Now test loader. So I'll use the same code. Data set here for this, I'm going to use the test underscore data set. So whatever you've named it, you should stick to that. You can't change it. If you change it, it's gonna be an issue. You'll be run into variable not found. You can either follow along with the one that I've used, or you can put your own variables. But be sure to uh, write the correct variables as you're doing. So now if you see, I don't need to shuffle the testing data set. Now that I've downloaded the data set, I've loaded it into the uh, PyTorch utility. Now I need to create a model. So let me create my CNN model. So the way I'm going to go about this CNN model is pretty simple. I'm going to create two layers, two hidden layers, and they'll have an activation function. I'm going to go with rectified linear RELU activation function and softmax function at the end for the output. So let me create class CNN neural network dot module. So now let me explain this model so you guys understand. You'll be like, okay, this made no sense to you guys. So basically, what I'm doing is I'm creating the CNN model. So it's going to have two hidden layers. Okay. And each of those hidden layers, I'm using a ReLU. You can see here, right? ReLU activation function. So this ReLU activation function is what I'm going to use for my hidden layers. So the input that I get is the image, right? It's going to be a channel with a lot of image. That output, I'm going to split it into 32. A single input is going to become 32 outputs. If you are trying to visualize, so one bubble is getting split into 32, and this 32 becomes 64. Now this 64, what happens is I need to pool it, but each of those is a 7 into 7 image. If you were seeing, each channel is 7 into 7 image. So I need to multiply that 64 into the 7 into 7 channel and then convert all of that into 128, so that 128 of them I have as a next output. From that 128, I need only 10. If it is 0, the first one out is the output. If it's 1, the second one. So like that, I have 10. So that's what I'm doing here. So this is the pooling function. This is these are all working with this. So what happens is here I'm initializing the model. So a good programmer always writes comments. So you are initializing the model. Okay. So here what I'm doing is, this is my first convolution layer. This is my first convolution layer. Now this is my second convolution layer. This is my max pooling layer, and what I'm doing is I'm downsampling it. So it's my max pooling layer for downsampling features. Now here what I'm doing is I'm flattening the size of the layers. So this is what is happening in my initialization. Now that that is done, here I'm correcting the flattening. If you see the view, right? So it's like minus 1, 64 into 7 into 7. I'm just correcting that flattening. And here what I'm doing is, here I am creating a activation function. I'm calling the activation function as you saw here, right? I'm calling that ReLU activation. Sorry. So this returns my output. So this is the class that I've created. Now let's go into, now that this is done, I need to initialize the model, determine what optimizers I'm going to use, and then the loss function calculation. This is very important. Based on the loss, we correct ourselves. So once I initialize the model, I'm initializing model. I'm doing loss function. Loss. Yeah, yeah. You can say loss function, and then I'm optimizer. This part is just for that. The reason why I write these comments is so that I can, in my head, I split it into blocks. Okay, this is doing that. This is doing this. So whenever I need to debug, if there's an error in the code, I can come back here and check it. Like, okay, it's this part is where the issues, or that part is the issue. The comments make it easier for a programmer to debug his issues, is bugs in his code. So now the model is my variable. I'm taking just some random model. So I'm going to use the CNN function, right? So CNN. Now here, what is happening is, now that I've called the model, I'm going to be sending it to my GPU. GPU is much more faster. So I put it device, as you saw here, right? Device. So this is what I'm sending it to my GPU. So it runs much more quicker than the CPU. Now, the criterion I'm using for this, I'm using the cross entropy, which is an inbuilt function in the PyTorch neural network model, which is nothing but a softmax function. So now here, now I'm determining the optimizer, what I'm going to use. So I'm put it as a variable. So there is this inbuilt function optin, as you saw here, right? I imported torch.optim as optim. So optimizer, so I'm using the Adam model. So what it does is, so I'm inputting the model that I'm doing, the parameters that are there, and then my learning rate will be the one that I've set on top. So I don't need to manually check in the code what the learning rate is. So here, if I just manipulate the uh, learning rate, batch size, and epochs in the top, it's more easier for me than individually going to each code. So I'm using an adder model, which is an adaptive learning rate, and it automatically adapts the parameters based on what I need. So now that this is done, now let's start the CNN model training, creating the loop. CNN model training. So now here, let me explain line by line what I'm doing. So I'll put the comments here. So what I'm doing is I'm initializing the loop, or I'm starting training loop begins in simple ways. Best ways, training loop begins. So now this here, this what this does is this initializes the loss calculation. Now this is where training loop, though the training loop begins there, including this is also the training loop with the image. Now this one sends the images to the GPU. So you're utilizing the GPU for training. So here I am setting gradient to 0. The model output is stored here, and here loss calculation. Now what this does is the backward pass gradient calculation. Now here I'm updating all the parameters to 0. Sorry, it just updates all the parameters. Here I'm getting the loss value as a float. Now here I'm just displaying each mean loss, each epochs. Oh wait, did I forget a bracket somewhere? Was not necessary. Where's it? Okay. What this does is it displays each mean epoch loss. Now that this training is done, we can test the model. So I'm going to create CNL model testing. So now I'll explain you what this does. So now I'm switching the model to evaluation mode. The function, switching model to evaluation mode. I don't need to train it. I just need to uh, change it to the evaluation mode. Now what this does is I'm disabling gradient calculation. I don't need it for testing it. It's kind of pointless. Now this is my testing loop begins. Now what I'm doing is I'm moving the data to GPU. Now this returns the output. So what this does is it gets me the what it predicts based on it after training, what it predicts the model to be. Now here what happens is this one, I think I wrote it in the wrong line. This one, so here this one just runs the model. Now it predicts what happens. Why we have an underscore is we don't need the image. We just need the label it predicted. So that's why we are writing it like that. So if you see that output data, we just need the label. We don't care about the image. We just need to know what it predicted. So now here we are appending based on that number of total images we have updates total images processed. So now we know total and how many are correct. So this by this is your ratio, times it by 100, you get the percentage of accuracy. So now the correct, so base if the predicted is equal to the label of what we know, then we add that it is correct. So we add that, we update the corrected one. That means we predicted one. So like that, it keeps checking. So how accurate it is, it keeps predicting and updates itself. So updates correct prediction. Now here I'm printing the accuracy is calculating because we have the total correct and the total number of images that are there. So correct by total gives you a floating point. You times it by 100, you get it in percentage. Now that this is done, now what we do is let's visualize the how it's predicting. So a sample, what is a prediction visualization, how it is actually thinking. So you guys have an idea. So let me explain what this does. So here I'm retrieving the batches of image here, retrieving the batches of test image. This code, what it does is it retrieves the batches of image from the test loader, since that's what you're using for testing. Now I'm only taking the first to visualize. I'm just going to show you for the first 10 images. To visualize, I'm just taking the first 10 images from the batch. Now here the first 10 labels also I need, right? So that I can compare both. Now that this is done, it runs to the model. This basically just runs the model. Here, as I told you before, what this does is it obtains the predicted model class. Now here, what happens is now that once we have run it from the GPU, I need to get it back to the CPU to visualize. So what I'm doing is I'm moving images from GPU to CPU for visualization. Now this is done. This basically I am actually setting up the plot. Here I am displaying the plot loop because for each 10, right? So I need to iterate at the first image, what is the predicted, what is the actual one, and what image it is. So for the first 10, I'm just creating the loop. So what I'm doing is I'm displaying the uh, uh, I'm actually displaying the plot loop. I'm starting it. So in grayscale, I'm displaying the image in grayscale. Here, what this does is it sets the title of each plot. Here, what I'm doing, I'm hiding the axis. I don't want to see those lines in the because this is image, right? Now here, this displays the full figure as a one figure with all the 10. And this runs the visualize function. So this is basically a program. So you can also save this model and run it. So let me just run this for you guys. You can see it in my console. Okay, where did I see? Oh wait, I think I made a silly mistake here. By mistake. Happens. So now that the program is running, okay, where did I label utilize? So see, when I run into issues like this, sometimes as a programmer, you're bound to make some typos and stuff. It helps when you have comments. So utilizing for GPU. So that's where I was. So utilizing for GPU training, I put labels dot device. Yeah, label. Sorry, here it's not labels. It's labels dot device. Yeah, that was my mistake. Okay, where did I make an error? Loss calculation output comma label. So this one loss is equal to wait. Again, this is the mistake I made. It's labels. Sometimes this happens. So criteria was never. Oh, that was my issue. Okay. So you guys also can follow along with me when I make mistakes. Okay. So wait, it was label. Okay. Running. So it's telling me it's using my RTX 4080 Super. So that means my GPU is running training. So epoch, the loss is being calculated. Wait, epoch is 0.2. So I think maybe in the why is it 0.2 printing it as one, right? Epoch plus one. Visualize underscore prediction. obtains the predicted model class. Oh, I put by mistake minus here. See, these silly mistakes you can. Now let's just see the epoch thing. Why is it 0.2? That shouldn't happen. So let's just check that too. Epoch. Epoch plus 1 by number of epoch. Wait. Oh, wait. I forgot to close this bracket, and that's why. I just. So it was actually dividing it for some. That's why. So let me just. I think this fixes that. Yeah. Now let's rerun it. So I'm using my device RTX 4080 Super, training the model. So yeah, now it's correct. Epoch 1, you see the losses being calculated. Epoch 2, losses being calculated. Epoch 3, see, you notice the loss is dropping as the next training goes on, Epoch. So that's a good thing. So training has completed. We had an accuracy of 99.01. So now here you can see the images. So predicted 7, it is also 7. You can see, right? This has been predicted as 2, 1, 0, 4, 1, 4, 9. This one is 5. See, this would have been a difficult one. It could have been 6 also, maybe it could have thought, but it's a 5 because it sees a stroke. And this is nice. So that's really good for my model. So this way, you see, it has a 99.01 percentage recognition. Other than here and there, that's silly typos and stuff. But you get the idea of the code, right? How it runs. And I'm using my GPU. That's why it's very fast. It ran so quickly. Now the same thing. If I don't use CUDA, let's say if I use the device, torch.device. If I won't use CUDA, let's say I use torch.device. I use CPU here. Now, if I use CPU, you can see the speed at which it runs. So it's running my code using device Ryzen 9 9900X, training the model. So you'll notice a big slow. You saw how quickly the first model epoch 1 was done. Now only epoch 1 is being done. It's still running. Now the second epoch is being done. And remember, I have a very high powered CPU, so that's why it still seems quick because it can handle a lot of stuff. But if it was any other normal CPU, it will take a long time. My GPU is also really good, so it was. You can see the difference. I would say the first one is like 16 seconds, and this one's taking 30 or something. So it's almost double the time it's taking. So training completely accurate. 98.98 is my accuracy. So yeah, so it's testing. See, it's predicting it all right. Yeah, I don't see any issue. So this predicted here, you see, it predicted it as 6 this time. The CPU predicted it as 6 rather than 5. So you can see these errors being. See, I ran the same code again, but you can get different prediction. So this is basically how the code runs. If you have any doubts, any questions regarding the code, you can just comment down. So my channel, I usually it's not a coding channel. It's something that I do coding for my work and stuff because I'm a biomedical engineer and an instrumentation engineer with experience in AI and machine learning. So I just thought when I started off machine learning and neural networks, I didn't. There were not a lot of resources online, and it was very dry subject. If you truly had it to, I was lucky that I had a wonderful professor who could, explain it to me really well. But that's not the case for a lot of students. So I thought maybe this will give you a. If you have a project coming up, you can use this, understand this. A lot of things is the base concepts. As long as you understand of neural networks, it's easy to implement it on different. You can use TensorFlow or you can use PyTorch. So it's just that you need to go through documentation of each to know the syntaxes and functions inbuilt in each of the different libraries. I use PyTorch because that's what I learned. You can use TensorFlow if you feel that is good, but the main concept behind it remains. A neural network has an input layer, hidden layer, activation function, pooling layer, and an output layer. For the output layer, you can use a softmax function. Depending on the different functions you can use, you could have even built the same code using sigmoid as a activation function. So there are different activation functions for different purposes. But I'm going off topic. I thought I'll just end the video here. It's already pretty long. So if you guys have any questions, do type it in the comments. If you like the video, do give me a thumbs up and subscribe. If you feel like I should put more neural network videos, just let me know in the comments. See you guys.